The next speaker is Leonardo Giusti. Leonardo Giusti is head of design project Soli in Jacquard at the Google ATAP. And he talked about in this presentation about the role of the AI, artificial intelligence, in the design process. If we are ready, we can start.
Hello everyone, my name is Leonardo Giusti and I am Head of Design at Google ATAP. Google ATAP is a research and development lab in Google devices and services. We are a group of engineers, scientists and designers that work together since the very early stage of innovation projects. And today I'm going to talk about one of them, Soli, Project Soli. Well, how many times you have walked into a building and someone has kept the door open for you, even if you don't ask for it? It happens all the time because as human, we have this sort of implicit understanding. And this feeling of being understood without saying a word happen all the time between people, but it never happened with technology. So what if we could experience a similar feeling when we interact with a product? This is in the end the problem that we're trying to solve with Project Soli. Can we design interaction that feel human? But let's start from the beginning. What is Soli? Well, Soli is a miniature radar sensor, a tiny sensor that understands human motion at different scales, from finger motion to full body movements. And it took us about 5 years to shrink this radar technology in a chip that can actually fit into consumer electronics, and to develop the software to interpret these complex human movements, starting from the temporal variation detected in the received radio waves. Why did we pick radar? Because radar has some very interesting property for consumer products. For example, it can operate at very low power, can be very efficient from a computational point of view. This allows us to create sensing system that can be always on, even in battery-powered devices. Then it works through material. So this is a good news for industrial design, because now you can create product that don't have any holes on their surfaces. And of course it's a more private than cameras, because it doesn't capture any visual image. It's also really robust. It's not affected by changing in lighting or temperature. It works during the day or at night in the same way. So this unique characteristic of radar unlocks some very interesting design opportunities. When we started working with radar, like at the very early stage, we focused on micro gestures. And we discovered that Soli can be used to detect sub-millimeter motion at the finger level. On the bottom left animation, you can see a range Doppler visualization where you can distinguish both two hands moving up and down, as well as two fingers quickly moving up and down. And on the right side here, you can see a prototype that uses machine learning to interpret this signal and actually create a knob-like micro gesture. However, very soon, we also discovered that with the same sensor, with the same chip, we could detect also larger movements, such as, for example, people walking around. You can see how in the left bottom image, it's actually a visualization of the raw signal, and you can see how you can detect people moving away and closer to the device. And on the bottom right, you can actually see a machine learning model that has been trained on that signal to understand when someone is nearby a device or not. So this is an exciting opportunity because with one single sensor, we can now create a new input method for consumer electronics that works at different scales, from micro motion to larger movements. And thanks to radar and some advanced machine learning algorithm, we can now interpret small and large gestures, as well as like body language expression, like, oh, I'm leaning toward a device, or I'm walking toward a device. And spatial relations between people and devices, like as simple as someone is nearby, or more complex activity patterns like social context and so on. So it's based on this observation that give us the idea to actually frame interactions with radar as non-verbal interactions. And we use these sort of like non-verbal communication cues every day. In our daily life, we use distance, body language, and gestures to mediate interaction with others. But despite the opportunity presented by our intrinsic understanding of these forms of communication, they have been rarely used in consumer electronics, mainly because of technological limitation. So with Soli, we want to create a new interaction language based on the continuous understanding of nonverbal communication cues. Over the past years, we have created a library of what we call interaction primitives. You can think them as pseudo API that can be standardized across a variety of products. For example, we have swipe and tap as two interaction primitives for gestures. You can have like approach or lean as interaction primitives for like body language, and like presence or the user status, is the user sitting, walking, as sort of like interaction primitives in the group of spatial relations. When you start putting these interaction primitive in the context of product design, they actually change the way we can think about the interaction with products in two main ways. First of all, they add natural gestures to existing input methods, such as voice and touch, opening the way to truly multimodal interactions. Secondly, they extend the relation between people and products beyond the direct active interaction, beyond direct manipulation. Thanks to Soli, now products can be aware of what is happening around them and actually anticipate the user intention to initiate the interaction. If you think about that, that is very similar to the way we interact with each other. Like when you enter a room, you are aware of the people around you, but you're not actually paying attention to them. However, if you want to initiate a conversation with someone, you need to first get their attention and then to start the conversation. So with Soli, we basically use a very similar approach to design interaction with products. And in these diagrams, you can see how our interaction primitives map against these new product states. Let's make an example. Imagine to have a home display like the Nest Hub. Because of Soli low power capabilities, it can stay always on and scan the environment to see when someone is nearby. If there is a notification, let's say about a delay on your upcoming flight, the device may decide to avoid the delivery of that notification at that specific time because no one is nearby. But then, when presence is detected, the device switches to the aware state. And now it may make the decision to actually deliver the alert because there is actually someone nearby to receive it. And in this state, the device can start looking for cues regarding the user intention to start the interaction. For example, if the user approached the device, like walking toward the device could understand this cue and expand the notification, reveal more information to the user. In this engaged state, the device can start listening for gestures. And now the user can easily dismiss the notification with like a swipe or take an action with a tap. So by introducing nonverbal interaction across Google portfolio, our goal is to create a new generation of product with social grace, Products that are not only intelligent, but also considerate of others, of the context around them. I want now to actually dive deeper on one of these interaction primitives to show what it takes to bring a vision into a product that ships in millions of units. When we start to work with radar as an input method for consumer electronics, there was no precedent in the market. And as you can see, it is really hard to build an intuitive understanding of how it works. So we literally had no idea of what would work and what wouldn't. So as designers, what we started doing was to run a series of studies, of interaction study, to get to know the material qualities of this new medium we were working with, even before start thinking about use cases and application. This is just an example, of course, but where we took a picture of the hand every time the radar reflected the same amount of energy. And then we superimposed these pictures, and this is the result. From this, we learn, for example, that a finger nearby the radar reflects the same amount of energy than your palm at distance. So, for example, the same gesture is actually seen differently from the radar point of view at different distances. And you can use this in your design, for example, to have the same gesture have different meaning when it's done close to the device or farther away from the device. We also started to build a simple interactive visualization so that we could start experience firsthand the relationship between movements and the feedback provided by Soli, and really learn about latency and responsiveness. And then over time, we start building more advanced prototype using mixed techniques such as heuristic-based algorithm and simple shallow machine learning models. Ultimately, we define a set of hypotheses, that makes sense, both from a technological and a user point of view. And we went out there and test them with people. We actually ran a study, an international study with more than 10,000 people across 13 countries. We really wanted to understand if this gesture had different meanings in different cultures. And so we went out there, we present these gestures to different people, and we discovered that independently from the device where these gestures were executed, there were some sort of like universal principle. Gesture with a motion, a main motion that was perpendicular to the screen surface, were often associated to actions, like pressing a button, for example. Gesture with a motion that was parallel to the screen were often associated with content manipulation, like vertical scrolling or horizontal navigation. And so we decided to organize our gestural language around this spatial model to make it easier for people to remember it and learn. And so we end up with two main gestures. Tap to take action, as it happens in the vertical plane, respect to the sensor, and swipe to move things around, as it happens on the horizontal plane, respect to the sensor. And these two gestures have been shipped in different products. As you know, discussed before, in Pixel 4, swipe were used for music navigation, dismissing alarm, and phone calls. In Nest Hub, we use swipe to snooze alarm and notifications. In the same way, the tap gesture was used in Pixel 4 to play and pause music, and the same use case was also applied to the Nest Hub that we just recently shipped. But how does it actually work? Once you have the gesture set and some initial prototypes, you're just at the beginning, right? The gap between a working prototype and an algorithm releasing millions of products worldwide is actually pretty big. So how did you get there? Let's take a look at the Soli software pipeline. The raw signal, as you can see in this diagram, is captured by the antenna of the Soli chip. Then different signal digital processing techniques are used to transform the signal in a format that is suitable for machine learning models. In our case, the range Doppler complex. Then we apply machine learning models to detect and classify these gestures. Here you can see on the left how the signal look like as an input of the for the neural network. You can see how it changes when a user performs a swipe. What you see there is a range Doppler, and on the vertical axis you have range, and on the horizontal axis you have velocity. You have positive velocity on the right and negative velocity on the left. And so we took, like, a screenshot of this visualization that you can see on the right side of this slide. And you can see, like, on the top row, it's a very clean swipe. You can actually see the hand moving away from the body, getting closer to the sensor, increasing the velocity, slowing down, and go back nearby the body. But then if you look at row 3 and row 5, the signal is not as clear. These are still swipe gesture, but especially in row 5, you can see that it's really hard to detect the hand, because the user in this case was performing the gesture very close to their bodies. So if you have to teach to a machine learning algorithm to recognize what is a swipe in the continuous flow of data that they receive, you need to show the neural network a variety of examples of what a swipe is. And you need to capture the variety of all possible swipes, like, for example, close to the body, farther away from the body, with the hand in this position, with the hand in that position, and so on. Because in the end, you want to be sure that the algorithm actually works in the real world, where people will perform this swipe in every possible way. And so a big part of this process is actually data collection. To simplify it a lot, you need to collect examples of swipes done by different people with different variations. We call these positive cases. But you also need to show the neural network what is not a swipe, even if it looks like a swipe. These are called negative cases. And on the bottom right, you can see an example of that. This became sort of like an iconic example that we keep referring during our process. We call it the coffee cup test. From a radar point of view, that motion is very similar to a swipe, but it's actually not. So the neural network needs to distinguish that motion from an intentional swipe. And you can do that by showing it a lot of examples of real swipes and what we call, the negative cases that are designed to trick the network.
The coffee cup test was just an example. In order to have enough coverage, you have to try and define a larger set of test cases that cover a variation of movements in different contexts and so on. So in the end, we end up designing more than 300 test cases for the data collection. And we collect data from more than 7,000 participants in 9 different locations across the world. We end up collecting 500,000 of gestures and more than 285 hours of negative recordings. So this massive data collection with some advanced machine learning technique allow us to achieve the performance that we needed to ship it into a real product. Ultimately, you want to have a machine learning model that have a high detection rate. Every time you do a gesture, it should be recognized as a gesture, and a low number of false positives. Where you're not doing a gesture, it shouldn't think that you're actually doing a gestures. And on the graph on this slide, you can see where our model was positioned. You really want them to be on the top left corner of this graph. So going back to our initial questions, how can we design interaction that feel human? I believe that the interaction model that I presented today, supported by Soli, is a step in this direction. Over the past years, we shipped some of these components in different Google products. For example, in Pixel 4 in 2019, we shipped the swipe, tap, gestures, the reach, and presence. More recently, in the Nest Hub, like a few months ago, we shipped the two gestures, swipe and tap, and a new building block, sleep sensing. It's a very exciting new feature that it will probably deserve another talk to actually describe how it works and what it is exactly. And finally, in the Nest thermostat, we ship presence for room occupancy. So it is, of course, our aspiration to make this interaction model, this new interaction language, part of the entire family of Google products. However, this framework is also important for us internally. It is a map that we use to establish a common ground between engineers, scientists, and designers so that we can communicate together. It is in the end a guide to orient our R&D effort toward the discovery of new interaction primitive based on radar technology in a way that is consistent across the different disciplines. Thank you very much. If you have any questions, please hit me at lgiusti@google.com. Thanks.
Hello?
Hello.
Can you hear me?
Yes, I can hear you. How are you?
Hi. Hello, everyone. I'm good. Thank you. And I'm sorry I'm not on camera, but my internet is really, really bad over here, so I have to take this on the phone.
Yes, I know, because Leonardo gave the confirmation before we change the original data of the symposium that was in May, but we have to change for some medical problem that the staff have got. And now Leonardo is in vacation, in holiday, and cannot connect to the webcam and is connected with the mobile phone, but is here with us. I start with a simple question. In the first part, in the introduction of the symposium, I speak about the role of artificial intelligence, and I speak about of the implication that TensorFlow library is carry on the design process, and I speak about is important and relevant a complexity that the designer can't control. There is a big gap with the use of the artificial intelligence to create a relation with the body and the ordinary ether of the design flow. And what do you think? Is possible that this gap will be reduced in the short period, in the short term, or remain a gap that control only the big company, or is possible that will be create some application that simplify this process to teach about the AI for create a new project that are for the everyday things?
Yeah, I do believe there is a trend where a new set of tools are becoming more and more popular so that people, designers, can just, start using them and create their own algorithms. But the problem with machine learning, and for example, there is products that are like already available, like Runway, for example. I don't know, it's not a Google product, it's another product that everyone can use it, and there is a lot of data available there, like GP3. There is like a lot of computer vision data available, and it's mainly used by artists right now. But it can be very well used by anyone to create different types of application. So there is a trend, I believe, to make this tool more and more available. But the problem with machine learning is that to make it truly open sources, you have sort of three main considerations to make. The first one is the tools and the framework. And with TensorFlow and TensorLite, they are already available. You can use them. You can use the power of Google Cloud to train your model, right? And then with TensorFlow Lite, you can export your algorithm in a very optimized form that can be embedded already in a device. And that's there, and is getting better and better over time and available to everyone. The problem, though, is not just the tools and the framework. The problem are like the data itself. The data are very expensive, and it takes a lot of time to collect. And in computer vision, for example, because it's an older field, right? You have 20, 30 years of history. There are a lot of databases that you can use to train new models. With other technology like radar, it's just starting, so you really don't have this data available yet. So the other important area here is to understand how to make this data available for everyone. And on one hand, there is the brute force approach, where you just collect huge amount of data, but recently, there are new techniques in machine learning called data augmentation that allow you to take few data and augment them, multiply them using certain techniques, so that you don't need to collect this huge amount of data like we did for Soli, for example. But data is still an issue that till you have enough people working on it, till they are made open to everyone, you still don't have them. And finally, there is the model itself, the algorithm itself, that it requires a lot of knowledge. There are certain model architecture, for example, for computer vision again, that are available and you can use them for different tasks. But for new input technology like radar, these architecture are radically new. And the one that we are developing now at Google are, we just published them. There is a paper we just published at CHI. You can go and look at them, but they're not yet publicly available. But that's our desire anyways, to make these models more available to everyone so that people can actually try them. So thinking in terms of like reducing the gap, I think tools and framework, amount of data, and make this model available to everyone so that people can train them for different tasks. These are the steps that are necessary in order to make it more like approachable.
Thank you, Leonardo. I pass the over answer.
Good morning, Leonardo, Andrea, colleague here with Michela. I bring you some questions from the audience connected on our online platform. First question from Fabio Pretini is asking, thank you. I was wondering at which maximum distance the radar is still able to detect, for instance, the presence of a person.
So it really depends on the radar settings, and which depends on like the power available to the device. But in a plugged-in device, you can detect presence till like about 6-8 meters. Yeah, 6-8 meters. On a mobile phone, which is battery powered, it has to be a little bit. It's less. It's about 1.2 meters. But with the current settings and hardware, we can push it to about 8 meters.
So that's opening the room for a collective interaction to this technology. It's not just personal interaction. Quite fascinating.
Yep.
There's another question for me, more about the perspective of this technology. And we talk about how to manage machines and the technology stacks to interact in new ways with technologies. But I'm wondering, if you believe that the mass adoption of non-verbal interaction technologies could influence our communication capabilities, you know, that's happened with text messaging, the use of text messaging, social messaging. We shortened our definition, we shorten words, and we are some scholars are observing that people take this language deformations and bring them into the real world, not only when interacting with technologies. So what's your perspective on that?
Yeah, no, that's extremely interesting. I do believe that, our effort, of course, is to take inspiration from the way people already interact with each other in the real world and try to understand those behaviors. But, from an technology evolution point of view, I do believe that eventually people will also adapt their behavior to be understood by technology itself. And this is often painted as a bad thing, And personally, I don't think it's a bad thing. I think it's an evolution of language. In the same way we adapt ourselves to use emoji and other forms of communication, I do believe that also our nonverbal behavior will change to interact with machines, and they will become part of the fabric of everyday life. The same way we interact with other people, we will have a sort of like code to interact with machines as well.
Thank you so much for being here.
Thank you, Leonardo.
Thank you.